Hi guys, welcome back to the channel. In this video I will be going through the alkanes topic of the A-level chemistry curriculum. So let's begin. Alright, so alkanes are hydrocarbons. What this means is they always contain carbons and they always have hydrogens. And the general formula for alkanes is CnH2n plus 2. So what this means is, and let's say we have 5 carbons, then what we would do is times that by 2 because it's H2n, so 5 times 2, and that would give us 10, and then we would plus 2, we would get 12. So the formula would be C5H12. So that's how we would work out the number of hydrogens and the number of carbons if we have to. So the fractional distillation of crude oil. So petroleum or crude oil is a mixture consisting of mainly alkane hydrocarbons. So the crude oil, which is a big source of fuel, mainly contains alkanes, and this crude oil is also called petroleum. But don't mix this up with petrol. Petrol is a whole different thing, which we will come onto later. And a fraction is a mixture of hydrocarbons. So again, the carbons and the hydrogens, and they have similar boiling points. Remember this key point, that fractions have similar boiling points. And the fractional distillation, which we will come on to, separates the fractions based on their boiling points. So it's the fractional distillation separates the different fractions on their boiling points. So how does fractional distillation work? So the crude oil or the petroleum is passed through the furnace first. So the crude oil goes in through there, and the furnace vaporizes crude oil. So if the crude oil is in liquid state, it would turn that into a gas, which is a vapor. You may not get the mark if you say it turns into gas state. So say it vaporizes crude oil, and the vapor is passed into the fractionating column. So from the furnace there, it's passed into the big fractionating column, and the column has negative, so it has negative temperature gradient. So what this means is this is hotter on the bottom, so near the bottom, and it's cooler on the top. So at the bottom it would have the highest temperatures, and at the top, as you keep going to the top, the temperatures would start to cool, and right at the top it would have the coolest temperature. So the fractions are separated by their boiling points. So as we know, the fractions they differ in their boiling points, so this is what is used to separate them in fractional distillation. And so the longer chain hydrocarbons, so which contain more carbons and more hydrogens, condense near the bottom. So they would go near the bottom of the fractionating column as they have higher boiling points. As you might know, that the bigger the hydrocarbon is, the higher the boiling point would be because of van der Waals forces. That's why it would go near the bottom. So again, if it was a small hydrocarbon chain, then it would condense near the top here. Okay, so remember this mnemonic: lovely people never kill dogs or babies. So you're meant to know all the different kind of fractions that a fractional distillation produces. So remembering this mnemonic, lovely would stand for LPG, so the gases, so that's near the top there, and then petrol, people, petrol, which is used in cars as fuel, never, naphtha, so that can be used in chemical making. Then kill is kerosene, or it's also called paraffin, but you can say kerosene, and that's used in jet fuel. Dogs, and that's this will stand for diesel, which is again is used for car fuel. Or is oil, which can be used in ships, so the fuel oil. And babies, bitumen, which is used in roads. So starting from the top, so you need to know in this order as well. So LPG would have the smallest hydrocarbon chain, whereas the bitumen would have the longest hydrocarbon chain. So LPG would be towards the top and bitumen would be towards the bottom here. Right, so the modification of alkanes by cracking. So cracking is basically a process where the larger alkane molecules are broken down into smaller molecules. So we're starting off, we might have a really big long chain, but then it would be broken down into smaller, many different chains. Right, so the cracking works by breaking the carbon to carbon bonds inside the molecule. So it would, from a big large molecule, it would break the carbon to carbon bond, and that's how it would form many different smaller molecules. Okay, so the fractions with shorter carbon to carbon chains are in more demand. So the longer carbon chains are not that practical, they can't be used in many things. That's why fractions with shorter carbon chains are in more demand by the petrochemical industry. Therefore, the longer carbon chains are cracked. So it's the economical benefits of the industries to crack the longer and larger alkane molecules to smaller molecules, which can be more readily used in many different things, as we have mentioned before. Alright, so you need to know, you just learn this table because there's a lot of questions which cover all this information. So you need to know the difference between thermal and catalytic cracking. So thermal cracking uses high temperature. Catalytic cracking also uses high temperature. You don't need to know the exact temperatures that are used, but it's just for comparison. And thermal cracking, again, it uses high pressure, whereas the catalytic cracking, it uses lower pressure. You can say slight or you can say low. And catalyst, in terms of thermal cracking, there is no catalyst, but there is a zeolite catalyst used in catalytic cracking. And intermediates, the thermal cracking has a free radical intermediate. We will come on to that after. And the catalytic cracking has a carbocation intermediate. Right, so the products and uses, you need to know this really well. So the thermal cracking, it would always produce a alkane, and it would always produce an alkene. It can produce many alkenes, but it would produce alkane as well. And so the alkenes can be used to make polymers, so such as plastic. And H2, it can produce H2. It won't always be produced, but the H2 can be used as a fuel. And so for catalytic cracking, you can have branched alkanes, and this can be used for fuels. And it can also produce cycloalkanes. So it would always produce branched and one branched alkane, and it would always produce at least one cycloalkane, and can produce more than one cycloalkane, but it would only produce one ever branched alkane. And it can also produce aromatics such as benzene, which has the formula C6H6. Right, so again, just learning this. So for when you have thermal cracking, so when you have the hydrocarbon, then you would only ever produce one alkane, and it mainly tends to be a linear alkane. So the opposite of the catalytic cracking, where you have the branched alkane, you would only really produce linear alkane in this, and you can produce one or you can produce more alkenes in the thermal cracking. You can also produce H2, but in catalytic cracking you would have one branched alkane, so only one ever branched alkane, and you can produce one or you can produce more cycloalkanes, and you can also produce aromatics. So the combustion of alkanes. So just remember that alkanes are used as fuel. And this is because the alkanes, when they burn, the reaction is very exothermic, as the bonds in the alkanes store a lot of energy, and when these bonds when the reaction takes place, it releases a lot of energy, which can be very useful. And so you can have the complete combustion. This will occur when oxygen is in excess, so when it's not limited. So the alkane, whatever the alkane is, would react with the oxygen, forming CO2 plus H2O. So this will only occur when there's oxygen in excess. Now you can have the incomplete combustion. So this is where there will be insufficient oxygen. So and the oxygen is not in excess, it's limited. So the alkane would react with oxygen. So in this time it'd be limited, and it would form carbon monoxide plus H2O. So because obviously carbon dioxide would require more oxygen, but carbon monoxide would require less oxygen. That's why this means that it's using there's insufficient oxygen. And if there is even more insufficient, if there's even more limited oxygen, then the alkane would react to form just carbon on its own. So this is solid. It's also called soot, and this can cause global dimming, which can have a lot of problems. We'll be coming on to that next. So carbon dioxide. So these are the problems of the gases, the greenhouse and the other gases that are released burning alkanes. So carbon dioxide is a greenhouse gas, which is produced when the complete combustion of petrol occurs. So we have octane in this case. So octane would react with oxygen to form carbon dioxide and water. Then we can have the carbon monoxide produced when there's insufficient oxygen, and the carbon monoxide is toxic. So again, the octane reacting, but you can see now we're using less oxygen. We only have 4.5 compared to the 12.5 we used earlier. And you can also form soot, which is the carbon solid form, which is a pollutant, and this uses even less oxygen, and this can cause respiratory problems, which can be really bad. So again, you can see this only uses 0.5 oxygen. And the reaction of nitrogen, so this usually occurs in the car engine. So the nitrogen reacting with oxygen, forming nitrogen oxide, or just any oxides of nitrogen can be really bad. And so this forms in car engine due to the high pressure and the high temperature. And just make sure you know this. And this leads to acid rain. And the unburnt hydrocarbon is also a pollutant, as some hydrocarbons do not react. The reaction isn't finished, and this can form a mixture of gases, which is also a pollutant. And the sulfur dioxide, which is also a pollutant, it causes air pollution and can form sulfuric acid by reacting with oxygen, causing acid rain again. So in this case, this is the sulfur reacting with oxygen, forming SO2, and that SO2 can react further with oxygen, forming SO3, which will be acid rain. All right, so catalytic converters. So these can be used. So what they do is they remove the pollutant gases from the engine. So the harmful gases such as carbon monoxide would be turned into less harmful gases such as carbon dioxide, and this is what the catalytic converter does. So it has a honeycomb shape, so as you can see there, and this increases the surface area, gives them a large surface area to be able to do their job more efficiently. And they have a metal such as a platinum, which catalyzes the reaction between pollutant gases to form less harmful gas, which will be released into the atmosphere. So if we did not have these, then the really harmful gases would be released, but these help out, and they would in turn make the really harmful gases into less harmful gases, which will be released into the atmosphere. So the carbon monoxide plus, so this is one of the reactions that occurs in the catalytic converter. So the carbon monoxide, which is again a pollutant, reacting with carbon monoxide, nitrogen monoxide, sorry, which can cause acid rain. So these two harmful reacting to form carbon dioxide and nitrogen. So nitrogen not being harmful at all, and carbon dioxide much less harmful than carbon monoxide and nitrogen oxide. And again, so the unreacted hydrocarbon this time would react with the nitrogen oxide, forming nitrogen, carbon dioxide and water, which is much less harmful. Right, so the combustion of hydrocarbons containing sulfur. So the sulfur dioxide produced is not removed from the catalytic converter. To prevent sulfur dioxide from forming, the sulfur should be removed from the fuel during manufacturing. So it can't be removed by the catalytic converter. And the SO2 can be removed from flue gases as they pass up chimney by flue gas desulfurization. So in industries, in factories, when the sulfur is burnt and the sulfur dioxide forming, it can go into the atmosphere, which can be really harmful, leading to acid rain. But there's something called flue gas desulfurization, which you can do to solve this problem. So what happens is sulfur dioxide is acidic, so the alkaline substances such as calcium oxide or calcium carbonate can be used. So for example, the calcium oxide can react with the SO2 to form a calcium sulfate, which can be used to make plaster. So the chlorination of alkanes. Okay, so a radical is a species with a single unpaired electron. So for example, it's chlorine radical, so there will be a large dot next to it to indicate that this is a chlorine radical. So this will have a single unpaired electron. So you can have, for example, fluorine radical, so this would mean that fluorine has a single unpaired electron. So or you can have nitrogen or anything like that. So this would indicate that it has a single unpaired electron. So in this case, we'll be covering the free radical substitution mechanism in chlorination. So this was the intermediate for the thermal cracking. This has different steps. So starting off, we have a initiation step. So this requires UV light. So this is one of the reaction conditions. Make sure you are aware of it. So this provides energy to break the XX bond, which is basically the bond between the haloalkane. So this is the CCl bond, CLCl bond, and UV light provides energy to break that bond. And the bond breaks, giving two radicals. So when the bond between the chlorine is broken, this would give two radicals of chlorine. And this type of this is called homolytic fission, because the bond between the chlorine is broken equally, so both of them end up gaining a radical. So again, this is the equation for it. So Cl2 gives two chlorine radicals. So the next step is the propagation step. So this is where the radical, so in this example, the chlorine radical would react with the neutral alkane molecules, producing new radical species. So in this case, the chlorine radical would react with methane. So methane, and what the chlorine radicals do, the any radical is a hydrogen stealer. It robs hydrogen from whatever there might be something present. So in this case, the chlorine radical would rob the hydrogen away from the methane, and this would form a HCl as well as a methane radical. So we only have CH3 now. That's why the carbon has a unpaired one unpaired electron. That's why it's a radical now. So now what happens is that same radical, this CH3 radical, would react again with that chlorine around the upper atmosphere, and now what this forms is a chloromethane. So the radical from the methane has reacted, so the carbon has reacted with the chlorine, and now it's formed CH3Cl, and now the chlorine becomes a radical because the chlorine molecule has reacted. So only one has reacted with the methane radical. That's why one is left without an electron. All right, so you might be asked for the overall equation. So you would have to cancel out things which appear in the equation twice. So in this example, the chlorine radical is at the start and at the end, so you can cross this out. So CH3, again, it's in the top equation, at the bottom equation, so you can cross this out, and this is how you would get your overall equation. So you have CH4 plus Cl2 from the reactants, and products is CHCl and CH3Cl. So you have a chloromethane in this case. And there is a termination step so this is where any of the two radicals come together and it forms a stable neutral molecule. So in this case, the chlorine radical reacts with the methane radical and it forms again a chloromethane. But you may not always form that chloromethane. So as the termination reactions, it involves any two radicals combining. So there's a lot of possibilities. So for example, the two chlorine radicals could react together to form Cl2, or the two CH3 radicals could react to form C2H6. So there are different possibilities. And so further substitution reactions can also occur. For example, the haloalkane product. So in this case we form CH3Cl. So what this can do is this can further react with other chlorine radicals, because we still have 3 hydrogens left, and the chlorine radicals are hydrogen stealers, they're hydrogen robbers, and they can end up getting this hydrogen, and this can form even CH2Cl and this can react further to form CH and this should be CHCl2, and this can further react to form CHCl3 and even CCl4. So until there are no hydrogens left. And you can stop this from happening. So if you do not want this to happen, what you can do is the further substitution can be prevented by adding the alkane, so methane in this case, in excess, and limiting the chlorine, and this would prevent or at least lower the number of further substitution reactions occurring.